Hello everyone, this is Hunor Chala. I will be presenting my work on modeling coupled 1D PDEs of cardiovascular flow with spatial neural ODEs. This is a collaboration between University of Utah and Los Alamos National Lab. I will be presenting this poster at the Machine Learning for the Physical Sciences workshop at the 2023 NeurIPS. Here I will go over the sections briefly one by one. Usually for doing cardiovascular modeling, we have a segment of a geometry like this one, for example. In this 3D domain, we solve the Navier-Stokes equations. However, at the inlet and the outlet, we have to prescribe certain boundary conditions. Usually at the inlet, we have a patient-specific inlet flow rate waveform. However, since these are patient-specific, these are hard to acquire, so there are a lot of uncertainties in these boundary conditions. This provides us a need for rapid patient-specific parametric blood flow modeling. Here in this case, we use an idealized stenosed geometry, and then we cross-sectionally average it to get a 1D model. In our 1D model, the main variables are the flow rate Q, the area S, and the pressure P. Here are the coupled PDEs for 1D blood flow modeling in deformable wall vessels. The first equation is the continuity equation. As we can see, the area S changes with time. The second equation is the momentum equation. For the inlet, we have this prescribed inlet flow rate. For the outlet, we have a resistance and we have an initial condition, but that doesn't matter as much since our dynamics are periodic in time. We have a constitutive equation for pressure, and our objective here is to create a fast physics-based, data-driven method for modeling coupled PDEs of blood flow in idealized stenosed arteries with deformable walls and realistic inlet flow rate waveforms. The main challenges are PDE coupling and time-dependent inlet boundary conditions. First, we generate data. We have a bunch of different simulations using a 1D finite element solver called Spatial. We have 54 simulations with different realistic inlet flow rate waveforms. All of these were generated from a reference waveform by Fourier series fitting. These are shown here. Blue color represents the training set, red the interpolation, and green the extrapolation set. Then we use neural ODEs to parameterize the right-hand side of the 1D momentum equation with a neural network. For the continuity equation, we use conventional finite differences. Our first approach was to use temporal neural ODE for the momentum equation. As seen here, we parameterized the right-hand side of the momentum equation with a neural network. We developed a differentiable ODE solver with the inlet boundary condition enforced in a Julia framework. Using this, we managed to get good predictions for the flow rate Q, as shown here with the spacetime diagrams. However, our predictions for the spatial derivative of Q, dq dz, were way off. And the spatial derivative dq dz directly appears in the continuity equation. That means when we are solving for the area S, we also get incorrect results. We refer to this as the smoothness and stability issues with the temporal formulation. Historically, neural ODEs have been used for space periodic PDEs like Berger's equation, Kuramoto-Sivashinsky isotropic turbulence. However, blood flow problems are periodic in time. Therefore, we had this idea to flip space and time and solve the neural ODE problem in space, as shown here. This way, the inlet boundary condition becomes the initial condition, and the solution will be implicitly smooth in the spatial z direction. We are still solving the continuity equation using finite differences. Using this framework, we managed to get accurate predictions for both the flow rate and the area S for unseen waveforms for both interpolation and extrapolation. The relative errors are listed in this table. As we can see, for both the area and the flow rate, the errors are below 1%. We've shown that casting neural ODEs in space helps with the inlet boundary condition with PDE coupling stability and solution smoothness. Our next goal would be to train with 3D models and develop real low-dimensional surrogates. I should emphasize that this is a generic approach applicable to a larger class of unsteady transport problems way beyond cardiovascular flows. Thank you for the attention. Here's my contact information. Let me know if you have any questions.